Let me start A back at 1. So notice as I increase A, it appears that the graph is getting thinner. What really is happening is that you're multiplying all the y coordinates by whatever A is, so it's growing that much faster. So in this case, if I multiply it by 3, not 33, then the ordered pair 2, 4, which was on the original graph, what just happened was you multiply the y coordinate by 3, so now this point gets shot up to 2, 12. In doing so, it produces a much, well, I should have just extended the graph. It just produces what appears to be a thinner graph. What I'd rather you think about it is when A is bigger than 1 or has an absolute value bigger than 1, you're taking the graph and pulling it away from the x-axis. Whereas if we were to make A a number between 0 and 1, so 0.6, 0.5, 0.4, so on and so forth, then it appears that it's being wider. In other words, vertically, you're compressing it towards the x-axis. Now, we have to say this correctly because notice if A was negative, let's make it negative, like, that's good. So I have negative 2.42 up there. Well, the A is doing two things. A being negative makes it reflect vertically, and A having an absolute value bigger than 1 stretches it vertically. So A can possibly do two things. So let's write all that down. The graph of y equals A times f of x is the graph of y equals f of x stretched vertically by a factor of absolute value, A if the absolute value of A is greater than 1. Or the flip side, compressed vertically by a factor of the absolute value of A if the absolute value of A is less than 1. So A could also be negative, so that also means there's going to be a reflection vertically. Let me make up an example real quick. Sketch a graph of let's say f of x equals negative 2 absolute value of x plus 1 plus 4. There are 4 steps that need to be done in a certain order to sketch this graph. Let's work inside out. We can go back to our inside out because notice the coefficient of x is 1. We don't have to worry about babies. So working inside out, let's apply the x plus 1. What does that say to do to the graph? How many units? Left 1. Good. Someone else? Let's work with the negative 2. What does the negative say to do on that 2? How? Good. And what does the 2 say to do, someone else? So you're multiplying the function by 2. Stretch vertically by 2. Good. And the last step, move up 4. What does the base graph look like? Not a check, a V. Let's do it this way. So if you move left 1, it would look like this. If you reflected down, it would look like this, right? So if you stretch it vertically, this point, the apex, would not change. You would just make it look thinner because you're stretching it vertically. So everything but where it touches the x-axis will move. Just that point on the x-axis stays where it is. So I want you to, I'll be right with you. I want you to, for these stretches, everyone's heard of silly putty, yes? It's literally like you stamped it and you're just going to go full. That's what a vertical stretch or compression is all about. Sure, I broke up A into pieces. I did the -1 first. And then I said you can multiply a function by any technically non-zero number. So this would generalize all A's. However, you have two portions to it. If A were positive, then it's a straight up stretch or compression. If A were negative, it's a stretch or compression along with a reflection. So we have, that's why this -2 here is broken into two steps, 2 and 3. Slightly better? So lastly, if we took this thinner version, the Drenny-Craig version, and then we moved it up 4, your final answer is something like this. Again, don't care where it crosses for now. All I'm looking for is shape and position. Is it a V shape? Yep. Is it at the right point? Yep. Works for me. The whole idea of this section is looking at a function and knowing what the graph looks like approximately before you throw it into the calculator. If you can predict what the calculator is going to give you, you're halfway there. That's fantastic.